This I learned in this book, The Crib Drag. This is, in this book, this really happened to the Russians. Now, you've probably heard of the perfect encryption scheme, the one-time pad. This is the one that has been perfect for centuries. There's no fixing it. What you do is you're trying to encode a bunch of letters, and you have a page full of just random letters. And you move each letter forward in the alphabet, like if it's A, you leave it alone. If it's B, you move it forward by 1. If it's C, you move it forward by 2. You use a different input key letter for every letter of the message, and you never repeat any part of the key. So there is no pattern at all in the output. And if I give you 100 characters encrypted this way, if you try to decrypt it by using all possible keys, you will create all possible sequences of 100 letters. You don't know which one is right. This is infallible logic, and as far as anybody has ever found, this is completely unbreakable. The only problem is you have to distribute a lot of key material. You have to have a whole book full of random letters, and you have to use a page and tear it out and never use it again. And that means you have to pre-distribute in a secure manner enough key for all the total length of all the messages you'll ever send. And that's difficult. And so what happened is in World War II, the Russians used this system, but they didn't have enough keys, so they started putting in more. They would type random letters on the keyboard and make one original and have carbon paper and have another one, and they started putting in 3 and 4 and 5 sheets of carbon paper to get multiple copies to distribute to people. And it turns out that if you send 2 messages encrypted with the same key, it shatters like glass and becomes trivial to break, which is interesting, and it doesn't take much of a computer to do it, and they did it in World War II with no computer at all. You could do it completely by hand. And so that's what I want to show you here. But here's how the one-time pad looks. If you want to encrypt a message like this one, unbreakable, awesome, secret, secure system, you're going to use this key to encrypt that message. By the way, you're already doing the wrong thing. Your key should be random letters, but your key could be readable English, and that does decrease the security of it some. And if you do that, this code will do that. Let me just run that, and you'll see how it looks. I'm running it locally. Nano, let me clear this. crib1.py. All right, this is the simple encryption. So I have a key string and a plain text, and now I'm going to make ciphertext here. So every one, I'm going to take the numerical value of the first letter and the numerical value of the first item in the key, and then do an XOR. This is not quite the Caesar cipher, but it's another way to combine 2 bytes to get another byte, commonly done. And so then the end result is you're going to get an encoded message. So let's run this one. Python 3 crib1. All right, and so you see it takes an F, which is 46, and a U, which is 55, and XOR gives you a 13, and then on it goes. So this is the encrypted message, which is a bunch of largely unprintable hex values. But that's it, and you can decrypt it with the same, as long as you have a key, you repeat the process with the same key, and it'll decrypt. So that's the system. And now, for the crib drag, I just programmed this and seems to be working. If I nano crib2.py, this is the crib drag. I have 2 messages encrypted with the same key. And I gave for this one, I said, I'm telling you the key starts with the word D. And so this just does it twice. It takes those unreadable hex values, XORs them with the bytes of the key, and prints out the answer. And I show you the crib drag attack. This is a loop, so it's interactive. If I run this one, Python 3, whoops, got to get out of here. Python 3 crib2. All right, so here I print. I told you it started with a key of V, and that gives you NEV and YOU down here. So that tells you it's working. And now, if I can guess the next character of the key, I can get another character of the output. So after the, if I assume the next character is a space, that's character 3, and it's a space, then I get NEVE and YOU apostrophe. And so the crib drag attack works like this. You guess any part of the key, and when you get it right, both of the messages will have a few letters turn clear. And then you guess where you go. After D comes a space, after NEVE probably comes an R. So you guess this one, you guess that one, you guess this one. As long as you can see, you can guess 1 or 2 letters on either side of what's clear, you can go back and forth. And even with no computer, it doesn't take too long to crack, which is amazing. It's perfectly, and this is the reason why people get so nervous about cryptography. This keeps happening. Cryptographic systems can be completely secure, but if you make any mistake in implementing them, even something that seems totally unimportant, the whole thing can shatter and become breakable. This happened with padding oracles, happened with many other things. The padding oracle attack used ECB mode, CBC mode, cipher block chaining, where you took the output of each block of text to be the random character to randomize the next block, and if you had an error message, when deformed code came in, that told you what the error was. If the error was incorrect padding, that's enough to destroy the whole system. If it just said, I reject this, it's bad, that would be fine, but if it gave you any more information about why it rejected it, that was enough to ruin the whole system. So this keeps happening. Anyway, this is amazing, not very hard to code, and you should check it out if you're interested. That's the crib drag attack. That's what I wanted to show you, and there's a lot of other things in there, but I thought that one was fun.